Yeah. Hi. Thanks for giving me the opportunity to talk. I'll be talking about SYK-like tensor models on lattice based on a paper which came out in May with Jungi sitting in the audience. So this is the kind of outline. I'll introduce, give some introduction and state the results. I'll then recall the tensor model, one particular version of it, and then I'll put the model on a lattice, and this will be the main part of the work. And then there are also some other. I'll also discuss some other models on lattice. Conclude with. Okay, so I really don't have time to describe what a SYK model is, but it's a model which was introduced long time back with some motivations from condensed matter physics, and but recently revived by Kitev. It's a model of fermions. It's a quantum mechanics of fermions. The disorder. There are n fermions, and the theory turns out to be solvable at large n and strong coupling. There are many interesting features of the theory, like emergent conformal symmetry, and which is broken, as Spenta was saying in the last talk. You can actually compute various correlators here, and it exhibits this very interesting feature that you can chaos bound and it saturates the bound, and that means that there could be a gravity dual about which there has already been work done, as again mentioned in the last talk. So I will be interested in something slightly different, which is tensor models. So you could ask whether the disorder is very fundamental to having SYK-like physics, and the answer is no. So this is an example. These tensor models are examples of theories which have almost SYK-like physics. So these are generalizations of matrix and vector models, as I'll show. But these are objects with 3 indices, so that's why they are called tensors, as against 1 index for vector and 2 index for matrix. These models were studied some time back with different motivations, but the connection to SYK was noticed last by these authors and others now. The and diagrams are similar to SYK, and you get almost same physics as SYK. And it will differ in a slightly, in some ways, which I will highlight later on. So SYK has been generalized in various directions. For example, you could turn on flavor, and there are supersymmetric versions, global symmetric versions. But here, versions of SYK. There are again slightly different versions of lattice SYK, but here I will consider one particular version which is closer to this paper by Gupke and Stanford in 2016, and we will consider tensor model versions of this. Okay, so I'll just state off the results in case you lose track, because this would be a lot of Feynman diagrams. So again, to reiterate, we study the tensor models on lattice. The formalism is quite general. It's in principle able to handle various different tensor models. We concentrate on one specific model, which is Klebanov and Tarnopolsky model, and we find saturation of chaos bound and also butterfly velocity. This is quite similar to this reference that I mentioned here. We can also study other models with these techniques. We can consider Witten's model, for example, and it turns out that the most efficient way to think about Witten's model is it as Klebanov model on lattice, this KT model lattice, as I will tell later on. And we, in fact, initiate a more systematic study of 4-point functions, more systematic than the original authors did, and we study their spectrum and behavior. Okay, so I'll start with the KT model, which is Klebanov Tarnopolsky model, which was introduced late last year. So this is not the first version of the model. This is slightly simpler, but appeared months later. So this is the Hamiltonian. This is a fermion, size of fermions. Fermions carry 3 indices. They're Majorana fermions, to be precise. And this coupling constant is chosen such that this theory has a good large n limit with finite j. It turns out that all these indices floating around, it's easier to keep track of it if you color the indices, and that's what I will do here. So I have given red, green, and blue colors for various, and you can see that this interaction can be represented by a tetrahedron Each vertex of this tetrahedron is actually representing a fermion, and there are 3 colors emanating from it, which corresponds to 3 indices, and they're contracted in a gauge invariant way, and this is a good way of thinking about it. Much more efficient than this explicit indices for many purposes. So this yeah.
There are lots of other gauge invariant vertices.
Yes.
Considered. Now the reason for focusing only on this one is presumably when this is marginal, all the other guys are irrelevant. Is that?
No, like there are other gauge invariant observables which are also the same dimensionality. It carries the same dimensionality. In fact, 4 fermion objects, but they won't give the large n limit of which is similar to. They give you different large n limits. So that's why I call this talk SYK-like tensor models. There are tensor models of various flavors. So if you choose some other interaction, it won't look like SYK model. So I am concentrating on those theories which look like SYK, which has large n SYK like physics.
There's no way that those guys might get generated? I mean,
RG flow wise.
RG flow, for instance? I mean, somehow you have to say that, you know, I can just stay put with this interaction.
Yeah, so we do, I mean, in general, the tensor model people do just exact calculation at large n. So we are not doing an RG analysis. So we just stick to this theory and you can just calculate everything. There is no divergences or anything. You can just compute these things exactly. But I don't know if there is a symmetry way of thinking about why other.
You have to break it a little bit because you are not staying exactly at the conformal point.
Yeah, that you put a finite temperature, but the Hamiltonian will be. Yeah, you can just calculate everything.
I'm just worried about the other terms getting generated or not.
Other terms getting generated. I actually don't know if a symmetry argument why other terms will not be generated.
I have not studied those terms. So
yeah, there are other terms, but you can just do an exact computation here and you can get away with just studying this. So that's my answer. Okay. So there is O(n) cube symmetry. In this theory, you can see that you can treat each index of this fermion to be an O(n) fundamental index, and it has some O(n) cube symmetry. We will work with large n and fixed A, but there are other works studying this model numerically in small n, which I'll not mention. No. So how do you do diagrammatics in this in this theory? So it's, as I told you, it's useful to think of this indices as colors. So you know, a fermion propagator would, you break up the single line fermion propagator into 3 lines and you give colors to them. And this is a very useful way of thinking about this theory. And then the interaction will be some kind of, this is this tetrahedron interaction written in slightly different way. So the scaling of this vertex is n to the power minus 3/2, and you can carry out diagrammatics and, to see what happens. So what's the nice thing about this kind of interaction is this, that there are what is so-called melonic operations, which keeps the n scaling same. So melonic operation is just taking this free propagator and replacing it with the melon, or what looks like a melon. And in terms of colors, colored propagator, this looks like this. And you can do a simple counting. This introduces 2 extra vertices. And I recall that there was n to the power minus 3/2 for each vertex. So that gives you 1 by n cube. But there are 3 extra loops. You can see that there's a blue loop, there's a red loop, and there's a green loop. So that gives me n to the power 3. So the net n scaling of this melon is n to the power 0. So you can freely take any propagator and replace it with the melon. It doesn't change the n scaling, and that is the class of diagrams that dominate at large n. So for example, in 2-point function, you can just start with free propagator and all its melonic descendants, where you replace each line by this melon, and they are all leading in large n, order 1. So here is a more, this is the 2-point function that one can compute. So psi I j k, psi I j k, all 3 indices are contracted here. And this scales like n cube to leading order, but you can actually do an exact computation. So I showed you some set of diagrams. This can be actually resummed to give you a nice closed recursive equation for a Green's function. So in single line, it is this Schwinger-Dyson equation, which is now, I think, quite famous because of the SYK work. It's the same Schwinger-Dyson equation as SYK, which in equations is this. So in strong coupling limit, okay, this G0 is just the free propagator, and G is the exact propagator, and this is a recursive equation you can write down for the 2-point function or the propagator. So in strong coupling limit, you can forget about the free propagator, and you can solve using a simple power law ansatz, and this is the answer. So J has dimension 1 in this, because we're working in 1 dimension, and this is the nice dimensionless combination that will always appear. Okay. So what other observables one can compute? One can compute 4-point functions. So here is a 4-point function. Again, the tensor indices look complicated, but you can just remember it by saying that these two fermions form a gauge invariant by themselves, and these two form by themselves. So you can call it Cooper contraction, never mind the name. So I represented this 4-point function by this kind of diagram. Again, this talk will have a lot of diagrams. So it turns out that the leading end diagrams are these kind of ladder diagrams, where you have some rung, and then rung is repeated infinitely. Of course, all the melonic descendants are of course the same n. So we can in fact resum the melons into a free propagator, so into a full propagator, and the leading end diagrams are just ladder diagrams made out of this full propagator. So this is the leading end diagram, and we can again write the Schwinger-Dyson equation, recursive equation, which looks like this. You can add this part to any ladder and get another ladder. So that's the recursive equation. I didn't tell you what this curly f is. It's just some part of this. It's like connected part, not exactly connected part, but subleading part of this thing. You will see slightly more detail when I talk about lattice models. But this is the recursive equation, and this K is like a kernel, and the kernel is given this object, which is made out of 2 propagators here and 2 propagators here, which is G tau 3 4 holes. Okay, so this 4-point function is quite useful to understand the chaotic behavior of the theory. So the chaos is diagnosed by studying the long time behavior of this 4-point function. This 4-point function is the same as before, except for these factors of p power minus beta h by 4, which is useful for regulating the answers. And this is in, sorry, I forgot to mention, all these things were in Euclidean time. This is an observable in Lorentzian time, so you need to do some analytical continuation, which you can do since you can solve this equation exactly, at least in the limit of large, the same limit that I mentioned before. You can forget about in the large beta j limit, in the large j limit. So for this KT models, this Klebanov Tarnopolsky models, it turns out this 4-point function has this following behavior. There is some constant leading constant, but then there is an exponential fall off, and there are corrections 1 by n, 1 by beta j corrections. But this the term can be computed exactly, and lambda L turns out to be proportional to 2 pi by beta, which saturates the K bound which was proposed 2 years back, and T star is proportional to log n, and this is a very long. I again dropped h bar and k here. So this is a quantum bound. So T star also has h bars and lambda L also has h bars. Okay, so now let me put the theory on the on a lattice. So here the fermions now get an extra index, this A index, which is now thought as a lattice index. So you could consider various possible models on a lattice. You could consider various of interactions, nearest neighbor interactions or next to nearest neighbor interactions or other kind of things, but we chose to focus on a particularly simple version where, okay, this is just the on-site interaction where all the fermions have the same index A sitting on the same lattice. Here is some kind of nearest neighbor interactions. This is not quadratic, but quartic interaction. Because quadratic interaction turns out to be not so interesting because it drives the RG to some different fixed point. So these are the kind of interactions one can turn on. there are three interactions we turn on to keep nice symmetry between the various colors. So this interaction, you can see that the same site is coupled via I1, which is a red line. So this is the interaction, and the two interactions have the property that same site fermions are coupled by green line or a blue line. So if we keep these three symmetries, there is some nice, if we keep these three interactions, there is some nice symmetry properties that we can keep. So this again, this model was studied at small n by a group in ICTS, but we studied it in a large n context. So again, the n scalings are important because you do the large n limit by taking the j is fixed and n to infinity.
L is arbitrary?
L is arbitrary, yeah. You don't need to, I mean, you're worried about whether you're taking a large L limit or not. No, we don't need to take large L limit, but it's useful to give results in large L where we go to continuous momentum. But yeah. Okay, so what are the correlators in this theory? So we can compute 2-point functions. So the 2-point functions will vanish unless the two fermions are sitting on the same lattice. That's just the property of this particular interaction that we have. When you have two fermions on the same point, on the same lattice point, there are various contributions to the 2-point function. This is the original contribution which came from the on-site interaction. This is from the nearest neighbor, where there's a neighboring site propagating in between. You also have another in which neighboring site you use a different vertex here that gives you effective coupling constant of this curly j square, which is the sum of all coupling constants in the theory. It turns out that you then get the same equation as SYK with this effective coupling constant, and you have the same solution, the 1 by j12. Okay, so now we can go on and try to compute 4-point functions. So it turns out that 4-point functions have a richer structure than SYK because there are various possible gauge invariant 4-point functions that one could turn on. So here is the closest analog of the original SYK 4-point function, which is this Cooper contraction that I told last time, where these two fermions form a gauge invariant among themselves and these two forms some other gauge invariant. So you can just see the n scaling of this is going to be like n to the power 6, which is kind of decoupled, and then there is subleading corrections n cube times this curly f, and that's what we will compute. But there are other 4-point functions available in this theory. So here, for example, is a pillow contraction. This looks like a pillow, at least from some angles. So this contraction is different from this contraction. Again, the indices is hard to keep track, but you can see that these two does not form a gauge invariant by itself. It's only all these things put together forms that gauge invariant. So this n scaling here is actually n to the power 5 because you can see that there is n to the power 5 free indices floating around. And the subleading guy is n to the power 4, and this is what we will compute later on. And for example, this is the kind of interaction one could turn on in the Hamiltonian, which if you turn on, you won't get SYK like physics. So this is just to come back to your question. The melonic diagram dominance, which was essential for SYK, only comes from the other kind of interaction, which is this tetrahedron interaction. But these don't give rise to melonic dominance, but you can compute them. They are gauge invariant observables in the theory. So here is another gauge invariant observable, which is just the same as interaction itself. Yeah, that gaps the theory. Yeah. So here I don't know, basically because it's too complicated to kind of. There is very few papers studying SYK with these kind of interactions. I mean, there is still some kind of diagrammatics at work, but I don't think anyone has calculated solve the recursive equation, for example. I think even recursive equation has not been written down yet. So maybe I'm wrong. So yeah, it might give different physics, probably. Okay, so this is the tetrahedron contraction. Okay, so now to compute 4-point functions, we will first compute this Cooper contraction, but for any 4-point function, you need ladder diagrams. How do you form ladder diagrams? Let's call these objects as dipoles. You string such dipoles together and you form a ladder. Now, dipoles can be of various types. For example, here is a dipole which transmits red color across the ladder. Here is a dipole which transmits green, and here is a dipole which transmits blue. So there are various kinds of dipoles. You have to keep track of all these things, but for now let's focus on this red dipole. One can do a simple n counting. So let me just go back. So, okay, here. So one can do a simple n counting, and you can see that there is one loop here. This is just the red loop, but there are two vertices, so that gives me 1 by n cube. So the net power of n is 1 by n squared. So the dipole scales like 1 by n squared, and you can try to see what kind of diagrams contribute to this dipole. And again, this is the on-site dipole which was there in the Klebanov model, Klebanov Tarnopolsky model, but these are new kinds of dipole what one will get, which involve various colors. For example, here the neighboring fermions are propagating in between, and you can compute the dipole, including the I'm factoring out the n scaling explicitly here. So these depend on what what values the two sides of the ladder have. If they have the same A lattice index on both sides, then it is this. If not, if it's neighboring fermions, it is this. If not, if it is far away fermions in the 4-point function, then it will be 0. So you don't need to take care of that. It's only the nearest neighbors that you need to keep track of. So here is the dipole. Now, what kind of ladder diagram contribute to the 4-point function? You can just try to string dipoles together and see what you get. So there are two kinds of dipoles. So this is unbroken, there are two kinds of ladder diagrams. One is the unbroken ladder diagram and one is the broken ladder diagrams. So the property of the unbroken ladder diagram is that one color transmits across the ladder. For example, here it's the red color which goes through. But the broken ladder diagram have this property that the color backs. For example, here the red color comes back, the green comes back, and the blue comes back. All colors comes back. Here one color goes through. So this is the difference between two ladder diagrams. And once you have these ladder diagrams, you can just see which 4-point function gets contribution from which ladder diagram, and then you can just sum it up to get the correct 4-point function. So here is the Cooper contraction. Again, this is the n scalings that I mentioned before. So it turns out that unbroken and broken diagrams contribute to Cooper contraction at the same order. One can easily see it for unbroken case because, for example, recall that each dipole has n to the power minus 2 scaling. But you can see that stringing this extra dipole here gives you 2 extra loops. For example, here it is blue loop and green loop which gets formed just because you added the dipole. That gives you extra n square. But dipole itself is 1 by n square, so it is the same order. It's not so easy for in the broken diagram also. It turns out that this 4-point function has the same n scaling as this. It's not very obvious. It comes because of external contractions, but you can check that's true. So this basically tells you that you can just sum up arbitrary dipoles. String arbitrary dipoles together to get this 4-point function, connected part of the 4-point function. And this is just given by this infinite geometric series with this all 3 colors together. And you can just compute 4-point function. It's the same as in SYK. So the 4-point, we can now work in momentum space by going, because this is a translation invariant system, you can work in momentum space. And this is the answer for the momentum space 4-point function. Here, so let me, F0 is given by this function, and P is the momentum, and SP is this particular function. You can see a dispersion here, and the K is the original kernel that I flashed in the initial part of the, in the original tensor model, and this is the same as SYK. In fact, SYK on lattice had a this Guki Stanford's lattice version of SYK had very similar, exactly same 4-point function. So you can read off the results from their calculations. So it has the same spectrum. Spectrum is like you can.
N has been absorbed in script J
square. Script J square here. Script J square already has an N because you scale the Hamiltonian in a particular way. That's okay.
Yeah. So you're when you sort of tied up two dipoles together, that's an n to the power 6 plus n cube.
Yes, that also gets removed because I explicitly scaled out n cube and I'm now calculating this curly f. There is no extra factor of n anywhere. I'm only, in fact, the dipoles were also defined without this factor of n. Ultimately there is no n scaling. All this are order 1 in large n limit. Okay, so have the same spectrum as this Guki-Stanford's version. Okay, so this is a CFT because there is power law scalings everywhere. So you can go to an OP limit of this 4-point function to read off the operators flowing in between, and you can extract the spectrum. So that is one interesting physics you can extract out of this 4-point function. And you can also extract the long time behavior, which gives rise to the chaos part of the story. So as I told you before, there is a e power exponential behavior in the, e power plus lambda L. There is an exponential behavior in the 4-point function, which now has a spatial spread. So this is a measure of the butterfly effect, how chaos spreads in spatial directions. And from that one can, from the spatial behavior of this one can extract a velocity. Both of them can be computed. It's the same as Guki-Stanford's calculation. So interestingly, the butterfly velocity kind of saturates a bound proposed by Sachdev and company last year, maybe 2 years back. It's the same result. Sorry, everything is large n. Large L.
Because you are using t minus ddx.
Yeah, you can do it in finite lattice also. Then it will be, instead of x, it will be some lattice distance. That turns out to be not very essential, but you anyway extract everything in small momentum. So for example, diffusion constant, you look at the coefficient of p square here, and you extract the small momentum answer. So I think it's not so much of a difference, but we can do this calculation in finite lattice also. All right, but more interestingly, there are other observables in the theory which actually was not computed in the original Klebanov's model or in the Witten's model. So these are these kind of pillow kind of interaction. I'm putting this again here just to make it more explicit. As I told you, this has n to the power 5 and n to the power 4, and we'll compute n to the power 4. Again, the ladder diagrams, you can analyze the ladder diagrams, and in this case, it turns out that it is unbroken ladder diagrams which are important. So instead of 3 colored dipoles, you will only have 1 dipole, and then you can just do a geometric series of it and sum it up. And I'm again extracting n to the power 4 to make these f's to scale without, to have no scaling with n. And you can extract a 4-point function. It turns out that this has almost the same behavior as the one in the previous page, except for this factor of 1/3. And very small difference here, the exact diffusion coefficient is slightly different, but no, there is no diffusion coefficient, sorry. Just the constants here are slightly different. But the main point is that there is a 1/3 factor here. And this turns out that this leads to no exponential growth in f. Unlike the other case where you had e power lambda L, here there is no exponential growth. And this is very interesting. You might just think that maybe this tells you that Lyapunov exponent is 0, but actually it turns out that that's too fast. What one should say is that the exponential behavior has not yet set in. So basically, this is just telling you that the scrambling time, which is the time at which the exponential behavior sets in, is bigger than the log n. That is the ratio between these two terms. In fact, in a very particular case, we could do slightly more, slightly better, which is not for this. This is rank 3 tensors where there are 3 indices. You can do a rank D tensor version of the same calculation, And it turns out that in this case, we can calculate subleading pieces here. Instead of 1 by n to the power 5, we can go even down. In that case, it's n to the power d minus 1 here, 2d minus 1, and then some series of terms. And in that case, you can compute, yeah, I'm almost done, just next. In that case, you can compute slightly more, and you can compute the Lyapunov exponent there, and then it turns out to be the same under some assumptions. Anyway, so there is one more piece of information which I'm not flashing here, but this gives rise to its own set of spectrum. You know, as I told you before, the previous 4-point function had some spectrum. Here also you can take an OP limit and calculate the spectrum, and that's a new prediction for the CFT. It's new set of operators which was not noticed before, and this was not actually computed even for the Klebanov model. So this is the first time computing it, and there are other tensor models that one can compute. For example, one can try to do Witten's model in this limit. In this formalism, Witten's model is just 4 fermions interacting with this interaction. It turns out that this method is useful to do computations in this more efficiently. In fact, one can see that our technique is useful to study any Hamiltonian which has some particular property that 3 of the fermions decide the 4th fermion in the quartic interaction. And in fact, this allowed us to construct a slightly general class of theories, models where Lyapunov exponent was non-maximal for some channels. So that's interesting. So I'll just leave it in this future directions. We think that at large D, there are some simplifications that's possible. And it's interesting to ask whether large D picks out some set of sub-class of diagrams. Are there other interesting tensor models? Generally, as I told you, the formalism is quite general. In fact, we thought of this was a fermion with the lattice index. So in fact, you could kind of generalize our formalism for fermions with any index. You could have flavor index, or you could have global symmetry, as Jungi kind of saw in his paper last month. So it's kind of useful for analyzing fermions with indices. Just useful technique. So yeah, that's the talk.
Guess about what?
No, actually not. Yeah, I mean, there is only one guess even for the original model. There's this 3D gravity thing that Sumit Das had, and I don't know whether there is something similar here. Yeah, but qualitatively the spectrum looks quite similar in the sense that if you remember, the original model had, SYK model had almost integer spectrum at large dimensions. Yeah. This is the case here also. It is just that there is a 1 by n correction, which depends on this coefficient 1 by 3 that I had. So it's quite similar at some sense, but yeah, I don't have any explicit understanding of it. It's a new prediction for whatever putative gravity dual you have.
And this appears on the 1/3.
Huh.
So how does that go to show that the Lyapunov exponent is 0?
Yeah, basically, I would say that there is no divergence in some sense. So, in some sense, that the whole crux of this calculation is that denominator vanishes at some particular point, and that point is where you have to do more careful analysis, and there you have to go to the 0 modes and do a careful analysis that like Maldacena did, and that gives you this e power lambda LT behavior. So here you just get some finite answer.
I mean, you were saying that you would still look at this k equal to 1 points. Why?
K equal to 3. K equal to 3. There is no k equal to 3 mode actually. Yeah. So that's the k is some function.
K equal to 3 just does not appear.
Just does not appear. Yeah. So you're not allowed to have k equal to 3. There's some spectrum which only k equal to 3 is not there.
So for finite L, so it should be a function of the lattice spacing.
Yes.
So simply lattice spacing or something else?
This x will be a. That's what.
X will be lattice spacing?
Yeah, x will be like a. Here you have the momentum space. You have to do a inverse Fourier transform to get it into the space. There you would just get X, I would think. Yeah, I would.